Here is a puzzle that has stumped physicists and philosophers for over 60 years. Mathematicians work in a world of pure abstraction. They invent new systems, explore strange structures, prove theorems, guided entirely by aesthetic beauty and logical consistency. They are not trying to describe the world. They are playing a game with ideas. And yet, over and over again, the games mathematicians play in isolation turn out to perfectly describe reality. Not approximately, not roughly, exactly. This is the puzzle, and nobody, to this day, can fully explain it. In 1960, the physicist Eugene Wigner wrote a paper with a remarkable title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner had noticed something strange. The mathematical tools that physicists use to describe nature were almost never invented with nature in mind. They came from somewhere else. From pure curiosity. From aesthetic play. From problems that seemed to have nothing to do with the physical world. He called it unreasonable because there is no good reason why it should be true. Why should the abstractions of the human mind match the structure of the universe? Consider imaginary numbers. In the 16th century, mathematicians encountered a problem. What is the square root of -1? The answer, obviously, is that there is no answer. You cannot square any real number and get a negative result. But mathematicians did something strange. They invented a new kind of number anyway. They called it I, the imaginary unit. They explored its properties purely as a logical game, never expecting it to mean anything real. 200 years later, quantum mechanics was discovered, and at its very foundation, woven into the core equations that describe every atom, every electron, every particle in the universe, is I, not as an approximation, not as a convenience, but as something the universe apparently requires. Consider curved geometry. For 2,000 years, Euclid's geometry was the only geometry. Parallel lines never meet. The angles of a triangle sum to 180 degrees. This seemed like objective truth about space. Then, in the 1800s, mathematicians began asking a purely intellectual question. What would a consistent geometry look like if Euclid's parallel postulate were false? They were not trying to describe anything real. They were exploring a logical curiosity. Bernhard Riemann, in 1854, developed a complete geometry of curved spaces. Spaces that could bend and warp in arbitrary ways. 60 years later, Einstein needed to describe gravity. He found that space and time are not flat. They curve around mass. And the mathematics he needed, the exact mathematics Riemann had invented as a game, was waiting for him, fully developed, on the shelf. Or consider group theory. In the 1800s, mathematicians studied the abstract properties of symmetry. Groups are structures that capture the algebra of transformations, rotations, reflections, permutations. It was beautiful mathematics, deeply abstract, apparently useless. In the 20th century, particle physics discovered something extraordinary. Every fundamental particle corresponds to a representation of a symmetry group. The entire standard model of particle physics, quarks, leptons, bosons, the structure of matter itself, is organized by groups. The mathematicians who invented group theory had no idea they were classifying particles. What is going on? One possibility